Testing, testing. Okay, testing, testing. Okay, test. All right. So we're going to talk about the reinforcement and why the reinforcement looks so great. Don't want to lose that image, but it looks like I am going to lose it. We're going to talk about why this reinforcement could look so great. Well, it can't look this great if a force was applied to it. A force that could cause a bending in it, a literal bending, a deflection. So we need to have the concrete fail around this, around it, without putting pressure and deviation on this rebar. Keep in mind, if you put 10 pounds of pressure on one side of anything, you're going to get back 10 pounds of pressure from the other side, ultimately. Meaning a piece of paper, you put 10 pounds of pressure on it in the air, of course it's going to break. But if you were to keep applying the 10 pounds of pressure on the paper and allow it to take its path, that is down to the floor or to the ground, ultimately the paper will stop and your 10 pounds will be met with 10 pounds of counterforce back at you. The paper may have a depression in it or may not. This shows none of that depression, if you will. So let's talk about what I think can help you explain this. Well, whatever we come up with, we have to have it pretty much that the concrete around it is in equilibrium, fails equally, and releases from around the reinforcement. Do not get confused with post-tensioning, Hooke's law, like a spring loading idea, with the rebar. The post-tension bar. The post-tension bar and the post-tension tendons are going to act in a different capacity. They're not going to be the same. For the most part, they're going to give you equal loading on each side of the bar. The tendons are going to have in this bridge are going to have different loading that's going to be on each end of the post-tensioning. They'll have a different force applied. The bar is equal. It's going to give us equal 288 kips, something like that, on each end. The bar has a plate on it. Has a plate on it. I don't want any of my mail popping up just yet, so let's just go ahead and get rid of this stuff. So the bar has a plate on it, which will act more like a nut, bolt and nut and bolt. With that said, the cone, pressure cone, is created a lot differently than typical. Could grab a different image. Just let me grab this one. So again, we talked about this in another video where I said it's the back of 12 that could have done this. I know you could probably also say the bottom of 11 did it. Bottom of 11 didn't have any gas in it, as I like to refer to it as, meaning no strength left. So I can't imagine it having the ability to do that. Also, you have to account for why the back of 12 is no longer present. The only way you can come up with that is a few ways. One would be this disintegration, this cone I'm going to show you. The other is bumping here. And that's about it, as I would say, Forrest Gump. That's about it. Another video, right? Let me just look at the thumbnails real quick. I love fiber. This is metal fiber. I'll get back to that. Another video, other channel. I'm going to race through this in a bit. Stone placement. As you look at the little thumbnails to the right if you're trying to figure it out. Let's try this. Works for me. So the this little blister here, this little add-on to the deck, needs to be resolved. It needs to disappear and leave this. How do we get that? There's a bar inside here. Now, Newton and it's simple physics, right? Is that there must be an equal and opposite reaction for things to become an equilibrium. So if you put 288 kips of anchoring here, there must be 288 resistant force back to it, thousands of pounds, 288,000 pounds resisting 288,000 pounds. This was done when they did this deck post-tensioning. They did D1. This is D1, and that's D1. This has a profile to it. These guys, D1 through D6, they're not all flat, as you can see pretty clearly in this image. They have a profile. They don't go straight across. I would run a line directly across them, which I don't have an image of right here. If I could run this line directly across, you would see that it doesn't work. I put it right underneath of that one, and then right underneath of this one. You would see the plane is irregular. Well, this was designed that way. And we'll go across the top of number 3, and number 3 here, approximately there. You would see that this is not equal, and this is a terrible image because it actually looks pretty darn equal to me because of the angle that we're looking at it. But what we're looking at more so is that everyone seems to be missing some beautiful stuff. So it's like a curve. And watch how I move this curve. I want you to pretend like this is post-tensioning. On this one, the forces would look like that, dead center. Let's do this. Let's put this dead center, and this one dead center. So I'm trying to help you understand post-tensioning, how the profiles work. Let's move that out of the way. I'll put this one in dead center of that now. You can see it's a slight dip here. And so when you post-tension this transverse cable here, for example, across, if they're all flat, well, it has to, this reaction is on this one, is at that location trying to deal with the post-tension cable that's above it. Hopefully that's a flat cable I've got here. And you see that this bridge, if you're looking at this angle, it's not quite, it's missing some materials at the very top. So I got to take a little liberty there, and so I'm going right here at the edge of the deck. There's the edge of the deck. I clip that section. I come to here since I got a flat point, and I try to make it parallel. Looks like I got to come down there a little bit. Tilt this end up a little bit. Drop the whole thing down. Almost there. Not quite. There's still a skip right here where my mouse is. Come down again. And it's still a dramatic skip. But you can see this bridge. This bridge is not flat. This structure up here is not flat, the image we have. So we're looking at a torqued image. This whole base has been torqued negatively or to the right, if you guys, clockwise, if you will. 12 o'clock here, 6 o'clock here, torquing that way. So I don't know, is this placed evenly or not? And this will give you some false data if you're trying to analyze it. But now analyze this. As you look at these 1, 2, 3, 4, 5, well, I don't know where 6 is. 6, it went over to 5 here. I don't know where 6 is on that one, but look at what you're looking at. Use your eyes and try to get you guys to help out. 1, 2, 3. I like giving hints. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Look where my mouse keeps moving around as I'm trying to do it. It's all over the place. It's up, it's down here to count this corner, and then this one over here, it's here. This one here, it's here. This helps you identify the curvature that I'm trying to help you see. Now, take really note of how the guy photographed it, or girl, and how we can see the underside of this. And in this one, it's got cement on it, so it clarifies itself a little bit more. This one, not so much. This one, we're looking more head on, and this one another way. So this bridge that we're looking at, the data we're looking at, is pretty damn torqued up. We would like to see if it's kind of in balance also, comparing the right to left, but we can't get that. Remember, a camera is going to have the sharpest data we're going to get out of all of these photographs if they're not cropped. If they're not cropped and not edited, the sharpest data, the best data is always going to be the center of the camera. I'm trying to think what cheap camera. It's probably a cheap. I saw this camera they had on one of the cameras. So the cheaper cameras, you're not going to have the professional cameras. You can do a lot more deviation, and in Photoshop, obviously, you can do a lot more deviation. But considering that these are unedited and they're using a cheap camera, our sharpest image is going to be here. Our least amount of distortion will be center of the photograph, of a non-crop photograph. And then as it tapers off in this direction, you're going to get your distortion going out to the corner. The most distortion down here, not here. The most distortion, the longest distance from the center are the corners. This is the plane here. You'll get distortion across that. And the defocusing part, it's kind of odd. It's where the lens is focused at. So that can be, whatever it shows, however the settings of the camera is. So it could be set on whatever's closest to the camera would give you a distance of it. A distance, a mistake in how you're trying to interpret things. I'm going to put this on each one of the bolts on the ends, 1 and 1. And now I'm going to run this to this bolt, and then this bolt, and then this bolt, this bolt, this bolt, this bolt, bolt, of course that one, and that one. Now I'm going to run to the middle of these guys approximately, and you see the profile forming there. It's a downward profile and downward, way up, way up. So big ass torque taking place here, which torque, a big ass, that's a technical term. Big ass drop is here, and externally, or apparent drop from here to there. That not just these cracks here, but this seems all sunken in. Now the transverse cables this is the transverse cables up top when they did this deck, and then longitudinal, these black hooded guys right here. And the transverse cables go across. They have forces in them that are pulling, are compressing in this direction from each side. On the outside of the deck in. Now you guys can imagine this whole thing is 2 foot 6 inches, roughly 2 foot 8 and 2 foot 6, all the way down the deck. All of these guys, 200 kips each, all the way down a 175 foot deck. All those forces want to equal out somewhere along their path, but ultimately, since they're balanced and their distances equally apart, right about in the middle. So all these transverse cables are creating a moment in the middle of this deck that has to be resisted. Okay, so all that, and I did that because I'm saying the forces create a bending moment. They're not just equal because they're countered by the this profile The loads are resisted by the profile here also. Whatever's down goes up, whatever's sideways goes sideways also. Opposite. With that said, since this is pulling in this direction, it makes a compressive end. But these caps here, these end caps that hold this thing from just breaking free, also create a tension in the backside of them. They have a tension they're trying to separate from, but the compressive concrete around it stops it from separating. But it's still a tensive moment back here going on behind these plates. Yeah. Behind the plates on each end, down here and here, as the forces are trying to pull inwards, this plate wants to flex. So you've got another force that is kind of sitting there, on these corners. I put it on the corners. And that corner up there, kind of sitting on here, wanting to do something here. Looking at bolted joints. So bolted joints on your engines and things like that. It's not typical, as I just showed you here, where I stated it's sitting there on the corners, and that's here. Where it's sitting here, it's a cone, a pressure cone. That is what they theorize. It's a theoretical pressure cone, but this is the way they've determined that the cone looks like, in a free body diagram, if you will, this graph. And so it would look more like, a creation of this triangle here, kind of inward and outwards, right? As you can see there, kind of like that. And we'll straighten that out a little bit. So it's got this plate on it. This clamp force, it's these tubes have been reported to be ducted, to be made grouted. Which changes it, it reduces the ability to slip, that's for sure, if it's grouted. But I state they were not grouted by the time they were post tension, because, well, they didn't show that as part of their process of grouting. I mean, of tensioning. They didn't say tension number D1 and then grout D1. That wasn't on there. So it's like a cone. Let's just take a little exaggeration of my beautiful artwork. So these forces around here, and on the opposite end, cutting to the chase a little bit for you guys, because I have to cut to the chase. This is B, this is A, and this is B. This is in the deck, and this is in the diaphragm, and out in that little blister hanging out there, the one that's missing out here, that's not present. This, you can imagine, is a cone here. This cone of influence is here and here. Cone is coming across here and here. That's a great amount of force that when this goes to fail, this is the part that will blast apart, freeing up this J-bar, and the same here. So this is what I think can explain the release of the concrete around it. And that would be here on this blister. So here's our point inside here. Now this is the true image in the air, and I didn't deflect this line. This is a straight line we're looking at. I put it underneath of here just by a clip. And let's do this magnifier. But remember what I said, that the cameras distort as you go to the outside edges. This appears to be closer to the camera than that end, so even that matters. But the profile is stated as such. It is stated that it will be profiled. So these are not designed, as you look underneath of the line there, not designed to touch each other. That one's touching, to be in plane with each other. They're designed, that one's deviating. They're designed to be up and down. With that said, they're supposed to be in equilibrium from left to right. So this one and this one are at the same plane. This one and this one is exactly at the same plane, supposedly. and the photographs are really bad, but I want you guys in other forums to really investigate how this should work. These are equilibrium going across. So yeah, this is higher in here than that one. But all I care about is D1s being in line with each other. If we could find a photograph of it cracked like hell, you can start seeing if the post tension and if this is failing, or do we have failure also of change of direction inside D1s, D2s, D3s, D4s, etc. This would have been data that would have been awesome to have when you were doing your analysis before they just started post-tensioning, to confirm that all these were at the same, that the post-tensioning didn't take on the new profile, which have been crazy dramatic forces going on there. So there's our cone that I just described to you. Now these cones will overlap each other to help you visualize it a little bit. Let's do this. Take a little liberty there. That's the default they're giving me on the length, so I'm not going to change the length on default. So that gives me my symmetry, if you will. Well, it looks like I just changed the length just then. Line it up with that. So this is the cone. There's the J-bar. You then duplicate the same thing down below. You start seeing these cones are starting to overlap each other a little bit. Starting to have a little conflict with some of the forces. I don't have the rotation one on that, so I'm just going to do that. So now if you look up Hooke's law, it will deal with the springing, the spring, and start talking about being equal in forces. But they don't deal with the loads at the end of the plates like this. It's just showing that forces are equal, proportional, and how to measure it. In this case, these are not proportional and equal because each end of this structure and the tendons have a different clamp force, a different ability. So don't assume that you start that you have one end of the deck figured out and you figured out the other side of the deck rather. So the transverse cables have different loads on each end, and so do the longitudinal cables. But the bars are totally imbalanced. They're equal with whatever force is applied to on one end is applied on the other end. It's a bar, not a spring, not a tendon. Okay, so this is what the force is, just giving you an idea of what, and you guys can look up look this up, I guess. Ball and joint analysis, mechanical calculations. Well, pressure cone is what it looks like. It's not quite the 45 coming off the edge of it, but I think there is a 45 coming off the edge of it. But their thinking is this. I'm saying, well, then what do you need the plate for? If there's no extra load coming out here, well, then we don't. This is extra plate is just on there for no reason at all. So I'm saying that the theoretical pressure cone is out here and not here. They're thinking, though, is your load. See the nut, the ball is actually, follow that down. There's the path starting here at the bottom, back of the nut coming through. But plate being thick enough, I think pushes it out to here, where with no deflection, it equally loads this and the pressure cone is out here. With that said, this is like the free body diagram. You see the loads are coming out here, and from what are they doing then? Well, they're bouncing back into the where the direction they came. So I would think that, yeah, there might be more loads here, and then it slowly tapers out to here. So, but nevertheless, it's still out there is what I'm driving at. So if you could extrapolate what I'm saying, leaving this like that, I now grab this one, and maybe I'll overlap it and show you a overlap of the forces coming off that plate, off the base of the plate using the 45 and pressure cone analysis, meaning I'll come back inwards. Now we're totally encompassing the J-bar right here. And we just crossed into this moment, this creating a moment here. very beautifully creating a moment here of all things. You know, you got to be careful of your biases. And so I'm biased at this point because if so, I'm corrupted. I'm corrupted in that I'm looking for a reason why a crack exists all over all the time. And the statement I'm about to tell you, what I'm about to give you, could be very biased. So you got to take it with your grain of salt because I would need further verification of this. But I want to show you a crack that's been driving me crazy that the pressure cone would resolve for me. And you know, I said I have to resolve every single crack, or I don't have it. You know, I'm getting close. I'm there, but if I don't resolve every single crack, I don't have it. That's my statement. I can't give you 90% of the cracks and say the other 10 don't count. They were created by forces, and if I can't explain those cracks, well then I can't explain the forces truly. I'm 10% out. That 10% could be 100% off. This crack here is the one that's been driving me crazy. This one. If you look at this for a trick, it's just 1 inch into the hole using this side of deck, or it's 3/4 using this side. So at 1 inch, I can use this line here and I come up 5.5. So the reality is about 4.5 inches off the deck, this crack. I can now line that up with the post tension bar and try to figure out if it's in line with that. I use that same 1 inch on this side. I come up here and I notice the crack starts deviating right about 8 inches and stops about 10 inches, which is really 7 and 9 if I take 1 inch off, approximately. I can verify that with the top of this, knowing if I can figure out where they place that. This is even with the top of this plastic. I then can go from 10 inches up to where it stops here, and this is where the direction changes. So I can say that's pretty much 4 inches, give or take, less than an inch. It's about a 4-inch crack. This is coming through here. Coming through here, though, is the path of number B, coming through. Down through here, just clipping. As B comes through the deck, I need to triangulate the deck. So here's the deck coming down. B clips through here and creates a small triangle of 12 sitting on it. This is the bias part I was stating because that's right about where I could show this crack, if you will. So somewhere on the other side, but there's the deck here. That's what I was trying to resolve. So somewhere like that. And this is the pressure cone, could create a tension crack, a pushing effect there, pushing 12 back away a little bit. We have the forces coming down, trying to keep this section in compression, though, also. So let's go ahead and put the other pressure cone on here, times 2. Whoa. You know what? That would have worked, wouldn't it? Nah. Pressure cone appears to be more angular in shape and not. The liberty I'm taking with trying to flex it would not be fair. I'm not trying to do any cheating there. I just I'm being lazy and just throwing them in, sort of making them work. So I'm not saying this is the exact pressure cone dimensions, because I would guess the pressure cone dimensions would change based on the pressure. So as you add 50 kips, the pressure cone is smaller, and as you get the 280 kips, I'm just going to balance it out. The pressure cone would get larger. So I'm taking liberty here. You guys you got access to triangles and all that. You can surely do your own. And I'm not hating for anybody doing it. I just sort of point the direction a bit. I'm just trying to see how bad my triangle's off by using a straight line, and they appear to be off pretty damn good. They're not. Well, they're almost parallel, these two. So this would be like your pressure cone area. As you can see, this pressure cone area comes back like this, and I'm very corrupt, that's the line also created on the deck. That would have that lifting effect of 12. I told what's his name? I forget his name. A man from Jersey. I said, give me a minute. You know, I got other videos I was going to show a counter forces in many ways. So this counter force is pushing up also. As it's creating a clamp force in this direction and a downward clamp force in the other direction from the other guy. Putting this member 11 in compression. But it has no choice but also to go through this decking area. And going through the decking area, this is roughly, so you can use a few things here. Hooke's law, you can use the cone and the bolt theory, which here's the back of the bolt, the nut. And I guess I should have moved that over just a little bit. Now the load path would be 45, so let's do that. Let's do that. I clean that up a little bit. My luck, I'm talking right now. There's no damn audio. Let me check this. Hold on. You guys got audio? Hey, Embry. Nobody trolling? I know. Well, you're here, Embry. Come on. No, I just dropped in here. 9 o'clock in the morning. No FIU bridge people. At 9 o'clock in the morning, I guess. Let me confirm my volume. Here, Embry. Yep. Oh, the delay is very small, too. So now here's our cone, and you can use Hooke's law, which is a spring deal, pulling back. Now, don't forget, though, if this is pulling that way, it's creating a tension in the back side of this. It's not for free. You can't just pull anything in one direction, right? You know, when you pull on something, it pulls on your shoulder at the same time. Well, I would theorize, and I have not seen it, that it's a reverse cone. That's my theory. If that's the cone there and everything's equal and opposite, we have a reverse cone going on, right? Well, we know it's not equal because it would have 280,000 pounds of force would just have blown this out. So or we have to determine that if everything's equal and opposite, then we have to determine what would it take to blast this off, and then say, well, this cone must be limited to this equal and opposite. It's just a thought. Or we say tension in concrete is not what we think it is, because they don't do tension in concrete properly. They don't do it as it really fails. They don't really measure tension properly. They use a splitting technique that I think this 10% rule of tension is way off. I go out on a limb with stuff like that, but I think it's way off. I don't think the way they're measuring tension in concrete is correct, because equal and opposite, equal and opposite, it's just weird, right? It's just weird that concrete can take 3,000 pounds of force in compression, and then it's determined that, well, on a tensile side, it's only 10 pounds. So that's because tension can be stronger than compression with a lot of cable, steel. Let's see, which one is that? I get them mixed up, but one's cast iron and the other one is shoot, I took you guys to the bridge in Philly. That's got the combination of both cast iron and the other metal, wrought iron. One's great in tension, one's great in compression. But we put one in tension and the other one, and you got yourself a quick failure. So it's just not all the same. We're not looking at everything the same. So this is this guy, giving you an idea of what's going on here. So here's the cone. Let's put these forces in here to help you visualize one more little touch. Remember, this is pulling down this plate. I'm going to stop that one right there. And let's put that right there behind the plate. So this is trying to compress this, go through here. And this is where you can imagine these forces are pushing out. So if you can imagine if there was just jello here, as you try to do this, this would bulge this outwards. And it only bulges it out to so far before it's a rebound effect, a theoretical rebound effect, since it's compartmentalized. And then we're coming back down to here. So what is that telling you? It's telling you, well, if this is already compressed, doesn't this make another load point that's successive in a cone? we get this, but then we get a multiplying effect right here that's not equal to the rest of the member because the cone's doubling back on top of itself. So you'd have to have a resistant force against this cone force by adding stirrups there between the cone force, backing off the cone force. I know it's quite complicated what I'm saying, but hopefully you can understand that. To make it equal out or cancel it out, you need to stop it. And you can do that with stirrups. This stirrup appears to be in line with our cone force. So, my theoretical cone force, and that's just by luck. I didn't do that. I did it live with you guys. I didn't do that trying to be biased on that one. Maybe subconsciously I did it. So you can see that would create a bending in a compressive moment in your stirrup system, right at the top of where they're interconnecting, sort of in that theoretical one. I just want to give you the cone thing again. Where you go, cone? Cone head. Oh, it's in a tab. Okay. So there's both the joint analysis, right? You guys can chase this down for some time. Here we go. This works for me. There's a cone again to the right. There's your cone. There's your zones. There's your pressures. It's your computer analyzed pressures. Here's another version of it. Then we have your spring and post tensioning. I was trying to find post tensioning in Hooke's law. This guy gets quite often wrong, so don't throw down with him so quickly. Oh, I also don't believe in the gravity formula to add to. So my bias is I don't believe in adding gravity to Hooke's law. I don't believe in multiplying 10 jack of nothing because gravity should have to be equal also. And gravity is too linear for me. It's an equal reaction. It's just equilibrium. That's all. You guys are upset by that. Then I troll. Then you just been trolled, and I get 20 points goes to me for being able to troll you. I have a new joke about being trolled now with points. So if Embry wins on a troll like he did the other day, I give Embry 20 points. We hear you. Hey, Cognitive. So my friend and I joked around. We were driving yesterday in the car. I was getting points from him left and right. I was purposely messing up his sentence, like I was repeating it back and getting it wrong. Of course, I was firing him up, and I was like, oh. And I was playing. You guys don't know. I play too much. So I'm like, oh, I get it now. You meant 12, right? Of course, he didn't mean 12. For example, he meant 10 because he said 10. And he's like, how do you get 12? I said, 20 points goes to Kai right now. Triggered alert. 20 points come to me. Like I owned him. I knew he said 10. I'm saying 12. And he's snapping. And then he's like, and I didn't tell him what I was doing about the 20 points thing. And then I'm playing it. I'm doing it for 10 minutes, man. I'm just owning everything he's saying. And he's like, I don't get it. You're not paying attention. I'm like, another 20 points goes to Kai. Total points, 500. And I'm totally, and he's like, that's not 500. You only did 5. That's like 100. And I'm like, another 20 points goes to Kai. So this is what I'm saying about how petty the amygdala is. And I'm trying to teach, guys, I love psychology. And it deals with, our psychology deals with the failure of this bridge also. Denny Pate could not have a psychological meltdown if they could not have a psychological meltdown. That means people would attack them, is what I mean. Not that they're going to have personal meltdown, but that it would have been such an ego destroying to them to have this bridge closed within 5 days to be set up. So psychologically, they all, not subconscious, and I'm saying not even subconsciously, they made a conscious decision to say, I better keep quiet because I know we should shut this bridge down. Well, you know what, Denny Pate, he's dumb enough to jump onto this bridge. His ego's so great that he's like saying, he's the engineer of this structure. If only he would have said, look, I think I made a miscalculation here. We need to stop. How many of you guys and engineers have done that? I've done it a few times. I'll go, I think I'm making a mistake here. Hold on. And usually people just want to keep running at that point. And that's when I scream out again, just hold on, stop. Let me think this out. Let me work this out. That's when you just stop. Just stop. Your direction, the data you're getting is sending you in the wrong path. So that's when you just stop. Stop. Just don't quickly, think you're going to, turn down the radio when you're lost and it's going to help you find yourself or speed your car up. Just you need new data. Pull over, reset. Get your data. Get your new data point. But ultimately, we do stupid things like speed up, like that's going to help us find our location faster, or turn down the radio. Obviously, turn down the radio helps you focus. But what I'm driving at here is that it's data, and sometimes we get data that sends us in the wrong direction. And let's go to and this is why they did not close down the structure. Is that their eagles all jump? Their triggers all jumped in. I can't be the one. I can't have messed up. So they try to fix it. Although Denny Pate's admitting that he's made a mistake because he's showing that he needs to do some repairs to it. But instead of them acknowledging it, going, "Great, Denny, you're admitting it, and you don't know what the cracks are," which they now brag about, saying that Denny Pate didn't know what the cracks were. Well, you guys remember that I stated that if Denny Pate or any engineer comes forward stating that, "Oh, I know what was wrong with the bridge all along," if any of them say that, then that means they should have known then also, and they should not have. They can't come forward. So all these engineers stating that that Denny Pate did not know, for example, OSHA, and at that meeting, Denny Pate didn't know where the cracks came from. They all should have said, "Wait a minute, you don't know where the cracks come from. You cannot be given an analysis on how to go forward from this point then. Until you know how the cracks came from, you just can't treat a broken bone, if you're just going to send a person right back into the broken bone factory where they just break bones. You can't do that. You got to find out what did it. The doctor's joke about it hurts. Why does it hurt? Because I keep doing this. And the doctor says, "Well, stop doing that." Well, in this case, they didn't care what was causing the breakage. They just said, again, they're too big to fail. So now I think I'm figuring out this crack here. This one here and this one. This is all part of the zone of the post-tensioning. And this is on 314 after the release of the loads. So the release of the loads, remember, everything's opposite and equal. And I said I would show this. These arrows here is going to explain it. So if this was holding everything together, because remember they did D1 first. So text D1, and I'm saying no grout at this point. So I don't care if they did grout. There is no grout at this point because no one's stating they grouted. Escape and delete and grab. So no one grouted D1. No grout at this point. And I want to say ones. I don't know. I just hate the word ones, believe it or not. It triggers me. Ones. Philadelphia, a lot of people say ones. It pisses me off. Ones, D1s. The D1 the ones just, I never understood that for meaning multiple things. Saying one and meaning multiple. To me, that's like a conflict. Those two don't work together in my brain. So that's not a pet peeve. That's some shit I got in my brain. So here's D1. So D1 comes across here. And let's change the color for D1 to a violet red if we can. And that didn't work. Let's go with blue. So D1 is coming across here somewhere. I don't know where. So right about here. You see where I'm going with this? So, but they do so we got text. But here it's designed with let's get a plate. So there's your plate behind D1 on the outside of the deck. So you're looking at D. Great, awesome. And it's got a little bit of bow in it. Oh, it's the middle. So you're looking at D1 right here. This is D1 and that's D1. So this is all they post tension so far. And then they're going to post tension this guy up here. A and B. B is the critical one, not A as far as I'm concerned right now. It does create a shear moment, I think. But that's another video. And, well, I guess I'll give you part of it now. But you see the crossing of that already between these two. You're creating a shear moment in there, but it's supported at this point in the staging area. In the staging area, it has shims underneath of here. So shims are all here holding this up. So nobody sees it as a problem when they go to testing, because shims with one S, right? There we go. So nobody sees it as a problem yet when they go to test it to release it. But Denny Pate did say grout the underside of this. But I don't think he understood the importance of it. I know MCM didn't understand the importance of grouting at that point. The reason why I said I don't think he understood it, because they were chasing it. They didn't know why. They didn't know why the failure was there. All Denny Pate did was point at MCM. Now here's one other option to that. Is Denny Pate did know that the shimming was the problem here, and he wanted to not throw MCM under the bus at the point, because it's a partner of his at that point. You know, you don't want to throw your partner under the bus, not knowing the bridge is going to fail. You would have thrown your partner under the bus, because clearly MCM is throwing Denny Pate under the bus somehow. Where are they? Anyway, they're fighting each other with lawyers. So I think so. Then I think we have the zone there. Where's the zone? So we got this guy, but remember they did a certain. This gets a certain detail to avoid conflicts of zones, conflict zones, huh? How's that? Conflict zones. And I'm going to use yellow. I got to start out here. See, the mouse changes, so I got to start out here. So this is their way of spring loaded, if you will, to conflict, to counter the forces they're applying in here to make it nice and even. No transition too bad, but it still doesn't really work, because this end of the structure still gets a higher post tensioning than, I mean, a less of a post tensioning than the opposite end. If you guys showed my other videos, I showed that this end is less than the one to the left, than the south end. So all the engineers and the other groups and everybody else talking about it, just look at the post tensioning schedule. It shows you that the south end and the north end are totally off by thousands of kips in their ability to support and make a clamp force. This being the least amount of clamp force down here. So you got this clamp force coming across here in D1, non-grouted at this time, and these are not grouted. Then they add the canopy, and that would be the canopy here. So canopies comes across, and that would be the same as the one down below. This would be this would be the same. These guys. So D1, no grout. I got to not do it. I was going to try to make it a box to make sure this arrow ties in with this, but I'm going to let that go. I can't. Bad habit. I don't want to let it go. I don't want to create a bad habit. I mean, all right. So then we got D1, no grout at this point. And I guess this would be a troll, because we know that's the canopy at that point. I'll leave that there. So, and D1. Trying to think, and or plus. I like plus in this case. Plus canopy C2. No grout at this point. So you got hollow ducts. So the clamping force is just tension in this whole thing, and you got a clamp force out here in the top are 12, and the outside of, oh no, I made that mistake already. It's actually in the canopy, not in 12. Does not have a bar through it. It's actually in the canopy, not the back of 12. It's on the side of 12. So don't get this confused with what I'm showing here, that this looks like it's in 12. It's in the side of 12, so that's actually up here then with the back of the plane with this. So I'll pull this in. So that's the clamp force there, creating that what I showed you earlier. When we get these guys going on here, you're going to get the same deal again. Or you're going to get Hooke's law, or you're going to get a combination of both. So you have to decide which one you're looking at there, or you're looking at a combination of both. Yeah, I lost it. But remember, they did add some. And this one, I'll do this one for you to give you an idea of what you might have to consider. Yeah. Right. No, that was right. Nope. Yeah, I'll do that. I'll double that back. So let's do this. So you don't forget. So you might have to consider that it's being canceled out by this guy here. But down here, we don't have that luxury. We just got reinforcement. So we got maybe some canceling out forces of the design up here in the trumpet area. But down here in the bar area, we do not. So this is looking top to that, top and bottom. So this creates a torque action too. You've got imbalancing on your twisting action, right? On your deck. So at least not forget this. These are just pieces put together with rebar holding it together until they put the clamp force in. So I know I gave you a bunch of data right there. So listen, this deck was done along with the blister. And then this was done. The tied in, only thing tying it at this point are the formwork holding it up and the reinforcement rebar. And then the canopy was built on top, and then the blisters. Now imagine right then, if you did not add any post-tensioning on any of the structure and you just remove the scaffolding, what's going to happen to the structure? It might stay in balance for a while, and then it's going to fall over. It would be beautiful to know which way it would go. Computer modeling obviously told them which way it would go, I would hope. And then they added the forces to stop it from going in that direction. Obviously, the computer modeling didn't work. What holds the whole bridge together at that point is the canopy keeps the decking, the canopy deck flat, keeps it flat by the post-tensioning in it. It also is held up and supports. Let's go to a quick image here of the rotate right. So rotate right, and I'm gonna end the video with that. I think rotate clockwise. So let's look at the pieces. We're going to look at it in my favorite way to look at it. So there's these guys. They're not in alignment. As you can see, this is up here. These bolts are here. These bolts are down here. These bolts are here. This is here. It has a weird-ass profile that goes in line and then drop down and then in line again. I think that, but it doesn't appear that way. Shit. I don't know where the VSL things were. I showed them in another video, the profile, and it shows that it's like a foot difference. It's major foot difference in profile, but yet I don't see a foot difference here in real life. That's quite disturbing to me. But you can see these aren't in alignment. You look at it straight up and down, you see they're not in alignment. And yet a crack like hell already took place. So are we already looking at a deflection in the deck? That this is already taking a torque downward. I wish they'd had more deck images. I swear that there's some cracking going on out here that they're not disclosing to us. Right here in this bad boy here. Oh, you know what? I could use this one, but let's use the scaffolding one because it describes what I'm going to describe much better. So let's get to the scaffolding. Oh, scaffolding. Oh, that's concrete testing, wasn't it? So rotate left. Here's your main post tension D1, 12-inch strands, 0.06. D1 right and left, as we talked about, how they did it. 23rd and 26th, the dates that they were done. Now, can you imagine if the canopy, if the scaffolding is not holding 100%, you're going to get a false reading as you do next. That scaffolding better be holding the 100%. Here's the whole, I was going to do a whole nother video on scaffolding and how it could have signaled, stated it's going to be canary in a coal mine. The scaffolding was. If you're post-tensioning anything, and as you're post-tensioning it, you evaluate the scaffolding. If it's becoming under compression, one side is becoming under tension of the scaffolding, it's telling you what that post-tensioning that you're doing right then, or what your post-tensioning doing right then is doing to your deck, where it's reacting. It's like a free body diagram offered up to you using the scaffolding. I always try to find something in real life, not to verify the forces, and I use things like scaffolding. Diaphragm 1, similar to diaphragm 2, except it was 3'6" wide by 4 foot deep. It is not similar. It is no friggin' way, and believe me, I want to curse, no friggin' way it is even similar. They're nowhere similar, the diaphragms. One is larger, one has 2 post-tension bars inside the deck. One has one in the deck, one going through, and one on a blister, if you will, that's in the deck, the deck pour. One has it going through partially through number 12. The other one on the other end has it not going through number 1 at all. They're not even similar. It's not even the same thing. One has a hinge, one does not. One has the 10 inches sticking off the deck, one does not have 10 inches sticking off the deck. One, the post-tension bars obviously go through a 3-foot member, and the other one, a 2-foot member. They're not similar. Engineering-wise, they're not similar. Diaphragm 2 was supported over 2 foot wide and 4 foot deep. What does 3'6" wide and 4 foot deep have in common? They got both 4 foot in common. They both say 4 feet. This one says 4 feet. That one says 2 feet. I would say 1 foot 6 inches is a huge difference in the base. I'd say it's a huge difference. So I find this to be nefarious in its wording. I'm never going to get that guy to compliment me again in my videos. I burn that bridge. Get it? Burn that bridge. All right, let's. Hey, this is for Embry. Okay, so there are the longitudinal cables. As you can see, this is the deck. Don't they all look like they're in alignment? This drives me crazy looking at this, then seeing what I'm seeing at the end of the deck with them going up and down, and also seeing what VSL stated the profile should be. But remember, Erica was reported to have changed the profile of the transverse cables, not the longitudinal, and yet I'm looking at this profile that's bugging me out. It's bugging me out. The data we're getting is not running true. Now, what the hell is this? If this is 1, 2, 3, 4, 5, 6, what the hell are these? D1 was 489 kips at the dead end. At the live end, it was 471 kips. Live end is where they post tension on our end of the deck. That puts it off in balance. So that shows it's not the same from diaphragm A 2 to diaphragm 1. Diaphragm 2, diaphragm 1, the one that's the larger one, has 489 kips on it, 489,000 pounds of force on that end. And on our failing end, we have 471,000. See, it's an imbalance in the deck. And now on the rest, D2 through D6, we still are in imbalance. We're coming up shy on the failing end of the structure. Down here, we're 745. That's an imbalance you're looking at. It's 175 foot long, 73 foot long. I'd love to know the elongation of each one of these. I find the imbalance in this post-tensioning to be wicked. All right, so getting to my darn scaffolding. Command right, clockwise. So scaffolding is the canary in the coal mine. If they would have, when they detention D1s, 20 points goes to me for triggering myself. Anyway, so D1s, they would have seen doing a survey, you can see the reaction in the deck, literally a survey of the concrete, which would have been the best way to do it. Or you can just use the scaffolding and try to figure out if you see any bowing or buckling, which would have been amazingly skillful if you could do that. You'd have to measure it, put a string line along it to see if it's deflecting, basically. The string line probably the best choice. Laser would be another one. It's just too many to do it. You just had a guy out here on a survey, on a piece of survey equipment. He'd be able to survey down here and sight down and go, hey, we got a deviation in the deck now. When you did D1, we got a crown here. Or when you did D1, we have a bow here. When you did D1, guess what? This took a torque, and number 9 or 7, it's now rotating to the right or rotating to the left. This stuff is sort of idiot-proof with that way. I don't like the idea of a string in this length, but even a string at this length, a cable at this length on the outside pulled tautly, you can measure the face off of it. That would be a terrible way to do it. Surveying equipment is the way to go. I own surveying equipment, so it would not have been a problem for me. And then now, so they do D1s, and then they turn around with the pockets ungrouted, because no one's stating they did, and then C2 in the deck, they do that. So they give rigidity in the deck and inside the canopy, leaving the scaffolding in place, as I understand it. Or did they take out all the scaffolding here on this area here, allow this to be loaded all the way down? That would be just point loading the scaffolding terribly so. Damn it, I want to know how they did this, the scaffolding or not. If they did that, that would just be crazy to do that. It would point load the scaffolding in the center, because all the loads in the canopy would then, without the post tensioning, would definitely be redirecting on C2, and also all these uprights, which would then be putting point loads on D1s all the way down this deck, because there is no D2 through D6 yet. So let's say that they left the scaffolding all in, they loaded D1, and then this. Why didn't they do, here's the question I asked you guys. Why didn't they just do number 11 and number 2? So I'm being facetious. So why didn't they do number 2 and number 11 first? Because clearly, I'm being facetious, clearly when you post tension number 11 and number 2, no forces will go down 10, and no forces will go down 3. So you don't have to do C2 or D1, do you? You don't have to, because all the forces, when you put this in clamp force with your post tensioning rods, just stay right out here in the ends. Because I'm showing you, they knew that that's not true. They knew forces were going down 10 and number 3. And they said, we only need a little bit of counter forcing for that. We're going to use D1 and C2 to help keep this rigid while we do that. Miscalculation, screw up, and they didn't add the post tension, the grout inside there at this point before they went to D1. Nowhere have I found anywhere they said post tension D1, C2, and then grout. I want to end this video with that, because this can go. I can run my whole system again for you guys as I give you all the data. I got tons more data to give you to prove, to make this. Everything's coming around to as I'm describing it to you. I can't, and I'm biased in a couple of things, but I can't make it fail any other way at this point. I can show the release of this being recaptured in the format. I can show that a lot of the forces were being. This was acting like a permanent brace here. Oh, I said that I would. Yeah. So I said I would do this. Let me go over this again. So before they post tension anything, these elements are just being held together by the stirrups and the steel from the deck to this nodal area here. That would be 9 and 10. And the same thing here from 12 and 11. It's being held by the stirrups and the scaffolding. The loads are. These scaffoldings, the loads on the scaffolding is not for free. Some of it is going down what? Down a pier, unequal to the rest of the system. Unequal to the rest of the system. They didn't keep this whole thing on a scaffolding. They created piers to support this. That's drama in itself. And then they start detensioning, and then they test loaded with the dead load, but with, I believe, with shims here, but definitely with number 2 and the number 11 post tensioned. So they never really tested it with it detensioned until they got it over the bridge. It just shows bad engineering. Just these engineers that suck. And if you want to find the engineers that suck, just go over to engineering tips. And some of you guys that are over there watching it might be fans of mine. I'm not talking about you. I'm talking about the others. So anyway, so no points either way in that direction for a troll point, for trigger points. So all right. So now they're over there having fun right now with the photography that I went over 1 million years ago about the pixels. And you could see, actually, if you get it down to pixels, you'll be able to determine what's going on with stability, what's actually being changed. They're still chasing after shutter lag, and I've already told you how you resolve that with just pixels. Now you don't have to do all that theoretical and wondering, and if you're going forward, this moves this a little bit. I saw their post on that, and I was like, man, I did that 1 million years ago, and I already told you guys how you do it. Pixels. You need the real camera, the real pixels, and I stated how the pixels show the moment this was actually moving faster than the rest of the deck using the pixels. You can then see when it gets balanced too, because it will come back to the regular speed that the camera can process. It's the processor in the camera. They got it down to the sensor only, and that's what one source, another engineer on YouTube, he's got it down to the sensor. It's the processor. Processor needs to work this out. Okay, sensors included. Sensors, your light distribution, and also how the pixels. And that's a big thing about pixels, about 4 pixels or 2 pixels or 50 million pixels over 12 pixels. Which one's better? Which one's good? That's a whole pixel argument. And I do have access to engineers with photography as far as the real development of it. And that's from a couple of the manufacturers. And I'm not going to market them at this point, but they do share with me how they're getting the data and pixels and all that. So yeah, that was very interesting. They also shared to me why they're stuck in looking like 35 millimeter cameras. Not what everybody thinks, but I'm not going to waste a video on that. Okay, so these are just pieces put together. If you were to remove this, I don't know how this bridge would fall. Towards us, the other direction, or that direction. I don't know how it would fall. Would it fall in the center and just buckle in the middle? I don't know. So this would have been a canary in the coal mine as they went along if they just simply surveyed as they did each as they did, added tensioning to it. But no, that wasn't in the budget or in the intelligence of the engineers there, including Denny Pate, Linda Fig Engineering, Berger, FDOT, FIU University. They put these silly ass sensors on there and said, we're going to monitor it through sensors. Well, old school surveying would be better because sensors still take interpretation, right? You don't need to interpretate a damn laser running down here saying, hey, you know what? The deck just crowned when you just put that last 50 kips on there. You're like, what? It crowned. What the hell's going on here? Ugh. And then, of course, this engineering department and everybody else will say, oh, that's interesting. Okay, I'm putting another 50 on. Let's keep on going. All right, so that's a facetious joke. I'm ending it. Hopefully this is helpful. I'm not going to go any further into everything, but you visualize the zones, the counter forces. Damn it. I want to show you one more. So as they detension this, the forces down here, we already know what it would, we already can extrapolate. They just released 288 and 288, or you can do half of that if you like and just call it 288,000 pounds. It grabbed back onto the back of 12 only. So you can extrapolate 288 times 1, because this is over here, I think we show no failure of number 1. So 288, this number 12 is being held up by 288 kips, I think it is, 288,000 pounds of force. which for it not to for it to do that, you also have to add 288,000 pounds of force downward. So it has to be to call it an equilibrium, or you get wait a minute, or you get cracks like this. Oops. Or you might get cracks like this one that I said, because this has too much of an uplift. A negative load is what I think I was going to tell whatever the guys over there. My brain's